Okay, guys. Welcome back. I hope you guys had a good Thanksgiving break. This is really, I guess, the last normal lecture you'll have, or at least for me. Today is on modern stochastic methods. So we're going to revisit SGD. And Wednesday is going to be a guest lecture from Aditya Ramdas, who I think many of you know. Aditya is going to teach you guys about mirror descent and possibly talk a bit about online optimization, depending on how much he gets through. And then Monday is, it was going to be originally a lecture I was going to give on a collection of non-convex problems that I found interesting. But then I've gotten some people in office hours and through Piazza asking me about more of like a recap, or maybe more of like a discussion of what algorithm to use when. So I figured I would just allow Monday to be any questions you guys want to ask. So it's going to be an open format. You guys can ask me any questions, limited to optimization, please. And I'm happy to try to answer them. And then if there's whatever time there's left over, we can talk about a few non-convex problems that I find interesting. And then Wednesday is your little test. So that's the rest of the semester. And like I said, today is kind of, I guess, a normal lecture, and it's probably the last one of this kind. Few announcements. Let's see if I can remember them. Okay, you have a homework due on Friday. Just to remind you, it's the last homework. And I made the last two parts, the last question bonus parts, just because I felt like you had a lot going on. And so if you already did them, you got bonus points. And if you didn't do them already, then you don't have to worry about them. You had your peer reviews were due over the break. There were a number of you that didn't do them, and because it was over the break that they were due, we decided to extend the deadline until tonight. So make sure to do your reviews by tonight at midnight. You know, it's part of the final project grade. It's actually a very small part, but still, it's going to be helpful to everybody in this class if we all do the reviews. So please do them. And the submission window is the portal, whatever, on EasyChair is open until tonight. Any questions about anything at this point, about what's left? Okay, so let's jump into today's lecture. So I have to thank Shashank Reddy, who helped me with make these slides. Shashank was my TA in 2012 for this course. I've had a lot of amazing TAs for this course, and they've gone on to do really cool things with optimization and otherwise. Aditya was another TA of mine. Shashank is now at Google. He's a researcher at Google, and he's done a lot of work in the area we're talking about today, both in terms of variance reduction and also in terms of adaptive methods, adaptive stochastic methods. So he's really an expert on the topic. I am not. I have a lot of material in here. We're not going to be able to cover everything in detail, but I wanted to give you a flavor of what people care about now when people are doing work on stochastic methods. And there's a lot of stuff that I'm not going to cover as well. I'm only going to give you a snapshot of what people are interested in, with a focus on variance reduction, because that's where the story is the most complete. I think at this point, it's a very recent and also a very kind of celebrated achievement in optimization, this idea of reducing the variance in stochastic methods for convex problems. So just to remind you about what we learned last time, we talked about this thing called the conditional gradient method. It's also called Frank-Wolf. And it was a kind of an alternative to projected gradient descent. So it also used just the gradient of our criterion function. But instead of making a locally quadratic approximation to our criterion, like projected gradient would do, and then projecting onto the constraint set, we just make a local linear approximation to our function, and we minimize it over the constraint set. That is the kind of key update, or that's the kind of the key step in the update. And Frank-Wolf then moves a bit in the direction of this minimizer. So if S was the minimizer of the linear approximation over the constraint set, then we would move a bit towards S from our current iterate xk minus 1. And we move actually less and less towards S as the steps go on. These are some predetermined step sizes that are the defaults in Frank-Wolf. We could also perform line search. The convergence is similar to projected gradient. We have essentially the same guarantees. It has a few guarantees which projected gradient doesn't, and a few characteristics which projected gradient doesn't have. So the first is that there are no projections, which is, it can be nice because in many situations it could be that this is simpler or more efficient than a projection. And another kind of key feature of Frank-Wolf that we saw that I find surprising every time I revisit it is that it's affine invariant. So it's very different in that regard from projected gradient. Okay, so today we're going to revisit stochastic gradient descent. And I'm going to just kind of recall some of the stuff that we went through when we talked about, we did a whole lecture on SGD when we talked about first order methods. I'm going to recall some of that as motivation for the rest of today. So the setting we're in is, let's suppose we're minimizing an average of functions. That's our function. And we're going to write these functions as fi of x. So our criterion is the sum of these fi functions from I equals 1 to n divided by n. It's an average of these functions fi. And this is a kind of common setup that you'll see in a lot of problems that involve like a likelihood data model in ML or statistics. So this could be, as an example, I could be thinking of a situation in which I'm doing regression, and maybe I'll use beta now as the optimization variable. Each one of these is just the squared loss on that particular example. So this would be like in regression, in which case this would just be least squares loss. That's what this would be. Or this could be classification, and this could be, as an example, the logistic loss. So these are maybe two examples you can keep in mind. This is classification. And if n is large, so we have a lot of data points, then our criterion is an average over many such functions. So, of course, what will gradient descent do? It would just take the gradient and follow the negative gradient at every step. And because we can commute gradients with linear operators, or in particular with the sum, rather, I should say, the gradient is just the sum of the gradients of fi. So full gradient descent, sometimes called batch gradient descent in this context, repeats the following updates. I have my optimization iterate xk minus 1, and I move in the direction of some amount, negative tk times 1 over n times the sum of all the gradients of all my functions. It's the sum of grad fi's. Stochastic gradient descent, or SGD, in comparison, just draws, let's say, one of these functions at random, uniformly at random. So I draw ik uniformly over the set, let's say 1 through n, equal probability, and I only evaluate the gradient of that function and I move in that direction. Okay. We talked about last time we learned this. We talked about non-randomized variants of stochastic gradient descent, like a cyclic variant where we visited each data point one at a time, and a randomized version where we actually drew this from the set 1 through n. In practice, it's more common to use something that's kind of in the middle, which is to take a permutation of the data points 1 through n and then visit the points in that order. So it's somewhere in the middle. The theory is somewhat easier for the fully randomized variant, where we're just drawing these IKs with replacement from this set. And the cyclic version is actually somewhat harder to analyze. So we're just going to be thinking about the version at which we draw these IKs with replacement from this set at every step. Okay, it's just maybe the simplest one to think about. And note that in that case, if I take the expectation of the gradient of f of ik, right, for any such drawn index ik, then I just get back the full gradient, because I have probability 1 over n of choosing any one of the indices 1 through n, right? And so its expectation is exactly this guy, and this guy is exactly the full gradient. So this f of x stands for the whole criterion here. So in other words, we're using an unbiased estimate of the gradient at every step. That's the way you could think about it. Okay, so also common, just to remind you what we talked about some time ago, is the idea of mini batches. So mini batch SGD is an extension of this where instead of just choosing, let's say, one index, we choose B indices. So we sample, let's say, B indices without replacement from the set. And B is something small. It's much smaller than N, let's say. Like it would not be scaling linearly with N. It would be scaling sublinearly with N. So it would be little o of N. And we'd repeat the following update. I would just evaluate, let's say, the average of the gradients of my functions over that set I, or capital IK, which has B elements in it. And again, for the same reason, we're approximating the gradient by an unbiased estimate. Okay, so we're doing something, we're not following the gradient itself, we're following an unbiased estimate of the gradient. And if you just look at, let's say, SGD, vanilla SGD versus mini batch SGD, what are the differences between the two? Well, they're both using unbiased estimates of the gradient, but mini batches reduce the variance of our gradient estimate by a factor of 1 over B, because we're averaging B things. So we have a lower variance estimate. It's still unbiased, so it sounds like it's a good idea. But on the flip side, it's B times more expensive, right? We're actually computing the gradients of B things rather than just one. So here's an example that we'll use to motivate. Actually, pretty much all of the lecture is just logistic regression. So imagine fitting a huge logistic regression where N is very, very big. And so calculating the full gradient is expensive. And this is the setting I wrote down here. This is the logistic loss. Imagine I have features xi and labels yi. Each of the yi's is binary. And if n is really, really big, then we don't want to do a full gradient update because that costs order np. And that's maybe, let's say, very expensive if n is huge. One mini batch update costs order bp, and one stochastic kind of purely vanilla SGD update costs only order p. Okay, so there's a big difference in costs, of course, when n is very big. So we're going to use the following set of experiments to motivate the rest of today. You've already seen these, in fact. You saw them last time. But I think that they're kind of, they're indicative of what happens at scale. This is a problem in which n is 10,000 and p is 20. So it's not actually huge, but this is pretty common as to what happens at scale. I'm showing you the progress of full gradient. That's in black here. Stochastic gradient descent. So that's in red, and mini batch SGD with a batch size of 10 and 100 in green and blue, respectively. And I'm just showing you the achieved criterion as a function of the iteration. So the first thing we notice is that actually these guys are not descent methods, right? They're not guaranteed to descend on the criterion. So we call it SGD, but we should probably not be calling it that. But I will anyways, because it's just easier and it's what everyone does. Whereas full gradient, of course, is a descent method, as we've learned. And we get this behavior where we tend to decrease OK. Let's say look at a mini batch size of 10 at the start. So we get this nice decrease in the criterion at the start. But then we kind of bounce around for a while. And the picture in terms of the progress close to optimum is, if you kind of think of an illustration where we have contours and this is the optimum we're trying to find, the picture is kind of like stochastic steps get us close pretty quickly. That's what this green curve is doing, or even this red curve is doing at a little later time. When they're in the vicinity of the solution, though, they tend to bounce around. Okay, we don't really converge to high accuracy at all. Whereas the progress is very different with the full gradient method. Okay, so mini batches help, certainly. It appears, at least in terms of the iteration, if you look at the number of iterations taken. But they're going to, whatever the mini batch size is, you're going to bounce around the optimum for a while. Okay, now let's reparameterize by flops. Let's see, rather than just looking at the iteration itself, let's reparameterize by flops. Remembering that somehow this is the cost of one batch update, this is the cost of one mini batch update, and this is the cost of one stochastic update. So we're going to multiply the iteration number by the cost of one iteration and look at what happens in terms of flops. So this is the picture we see. So it's very, very different. And in fact, mini batches, if we somehow were to extrapolate and track the progress of SGD versus mini batch with size 10 and mini batch with size 100, it looks like it's almost a wash. Once they get to somehow a reasonable spot around the criterion, it's like they're tracing out the same convergence curve. So we're reducing the variance of our gradient estimate. We're paying more per iteration, and it looks like it's pretty much a wash in terms of the conversions. Okay, and still, batch gradient descent is still much more expensive. So we see we can achieve very reasonable decreases in the criterion in a small number of flops, even less than somehow like one gradient descent update here. But we're not going to be converging to high accuracy. And that's actually exemplified by this picture. So now, instead of plotting the criterion itself, I'm plotting the gap in the criterion at iteration k versus at the optimum. So f of xk minus f star. And we see this picture, okay, which is actually explaining quite a lot. Here, we have a problem in which p is 10, n is 100. And the logistic loss, let's say, it's strongly convex on its sublevel set. So if I look at all of the points, I pick some beta 0, like I pick beta 0 equals 0, and I look at all of the points for which the logistic loss is less than or equal to what it was at 0. That's some compact set. Okay, it's convex because the logistic loss is convex. And the logistic loss happens to be strongly convex on that sublevel set. And it's never going to leave that sublevel set because it's a descent method. So actually, we're in a situation where the criterion has a Lipschitz gradient and it's strongly convex, and we get linear convergence. Okay, with gradient descent. This is on a log scale, so we see this nice linear convergence. It converges at the rate like log of 1 over epsilon. These guys aren't even coming close to converging, even at a sublinear rate here. They actually look like they're bouncing around. That's because I chose fixed step sizes. If I chose decreasing step sizes, then you'd see a slow sublinear convergence. Okay, they would look very similar to this, but you'd be convinced maybe that they would still be converging in the end. Okay, so I guess we're looking at this picture and we're asking now, have we hit the limits of performance for SGD? Is this the best we can expect in terms of stochastic optimization? Let's turn to the theory now to see whether it matches what we see in experiments. We went through, of course, for the first column, we went through all of these in lecture, and in fact, we proved at least the latter two, or at least the middle one on the homework. I think this one was a bonus on the homework, and this one we maybe put some part of it on the homework for subgradient method. But you've seen all these, just to remind you. For a convex function, if all I tell you is that a function is convex, gradient descent converges at the rate 1 over the square root of k. So in k iterations, this is the decrease it sees in the criterion. This is because in the absence of any other assumption, we kind of appeal to the analysis we have for the subgradient method, which is gradient descent for a smooth function. And this is the rate we got. As soon as I add on top of convexity the fact that my function has a Lipschitz gradient, I get a 1 over k rate. And if I add strong convexity on top of that, I get a linear rate. So in k notation, that's c to the k for some constant c less than 1. Okay, which is in fact what we saw here. This is on a log scale. How about for subgradient descent? Stochastic gradient descent for SGD. So I referred to these. We didn't prove these, but I referred to these in lecture, and I can point you to the papers that provide these bounds. They're fairly straightforward analyses. It's fairly similar to what we do for gradient descent. But we see something really different and kind of disturbing, which is that in the most basic case, we match the convergence rate of gradient descent. We get back the 1 over square root of k rate. But it does not improve once I assume that the gradient is Lipschitz. So that provides me kind of no improvement on the rate. It's still 1 over root k. And most disturbing, as soon as you add strong convexity, in addition to Lipschitz gradient, we get a sublinear rate. We get 1 over k. We don't get this very fast decrease of c to the k. Okay, so let's dig in just a little bit as to why that is. I'll try to give the intuition for it. In gradient descent, if you remember that in both of these cases, we took, both for Lipschitz gradient and for strong convexity, in both of those cases, we were allowed to take fixed step sizes in gradient descent. Okay, and we actually proved that such step sizes were convergent. So in the case of a Lipschitz gradient, we're allowed to take t to be 1 over L, where L is the Lipschitz constant of the gradient. In the case that it was additionally strongly convex with parameter m, we took them to be 2 over L plus m. Okay, but in both cases, they weren't diminishing as iteration counter k increased. That was what allowed us to kind of have such fast convergence, because we do not somehow halt the progress of our algorithm as we get closer to the solution. Right? We take fixed step sizes, we're allowed to kind of make big gains late in the iteration counter, which allows us to converge to high accuracy solutions. For this rate, if you recall, this was done under the subgradient method analysis. We had to take diminishing step sizes here. Okay, we took them to be like 1 over k as an example. tk equals 1 over k. That's how we got this rate 1 over the square root of k. That's how we actually proved it was convergent in this case. For subgradient descent, you can never escape the fixed steps, the diminishing step size setting. Okay? If you take fixed step sizes, subgradient descent is not going to converge in general. I keep saying subgradient descent. Stochastic gradient descent. I should say SGD. SGD will not converge in general under fixed step sizes. That's what you're seeing here. Okay, with diminishing step sizes, it's going to converge, but it's going to converge very slowly. And we need to take diminishing step sizes to control the variance of our estimate of the gradient. Okay, essentially, without taking diminishing step sizes, we're going to have non-trivial variance, which means that when we're close to the optimum, we're not going to be following the gradient. And if the gradient's very small, perturbations around that are going to be very bad, and we're not going to be converging. Okay, so we need to take diminishing step sizes to control the variance of this estimate. So the way you might think to do that is to take larger and larger mini batches, right? That decreases the variance by a factor of 1 over b. But you're paying essentially an equivalent cost in terms of computation. And what you see for the rates of mini batch SGD is that if I were to somehow look at the progress per flops, per flop, it's exactly this. It doesn't change what happens in practice. It doesn't change what happens in the theory. It's completely a wash. Now, in practice, they're still popular. I don't want to kind of say that people would never use them in practice, but that's because of communication costs. Okay, it turns out that it helps to draw a sample of data points rather than being kind of communicating constantly to pull one data point into memory to perform a computation. So they just help communication costs, perhaps some other things in practice, but it's not because of faster convergence in this regard. So again, maybe, as of, let's see, 4 years ago, people thought this was the end of the story. Is that right? 2014, I think, was the first paper. People thought that this was just the end of the road for SGD and for stochastic methods in general, and that we could not hope to adapt to strong convexity. We'd be stuck with this. This is what we have to live with, and that's about the best we can do. That's because there's a famous paper by Nemrovsky and several others in 2009 that established matching lower bounds. So it said that for a strongly convex function in a stochastic setting, if you have strong convexity and Lipschitz gradient, you should be expecting this. Somehow there's a problem instance, for any algorithm, there's a problem instance for which the algorithm cannot be converging faster than that. And Nemrovsky is an extremely famous guy. I mean, he's done work for decades on optimization. This paper was very influential. And people were just kind of resolved to the fact that this was the lower bound that they should trust. But if you looked at that paper carefully, that was for actually quite a more general setting, okay, where the criterion that we're looking at, instead of being an average of functions, it's actually, let's say, an expectation of functions. So it's quite a more general setting. So I have some function, let's say, capital F of x and some randomization variable psi, and this is an expectation with respect to psi over some measure p. In our setting, this p is just like a discrete distribution, right, supported at a bunch of functions fi, and so this expectation is an average. People in optimization call this a finite sum. And what happened around the time 2014 is that people realized that for these problems, which are really the ones we care about in ML and statistics, this lower bound is not, it's too conservative. So the construction of the worst case function given any algorithm, it doesn't apply to finite sums. It kind of requires this generality. So we can hope to substantially modify SGD in order to get faster conversions for finite sums. And that led to a bunch of nice papers, I guess around the time 2012, 2014, that had to do with this variance reduction principle. And the takeaway message, I guess if you have to remember nothing else in this lecture, is that with variance reduction for convex functions and finite sums, you can bring SGD from this column to this column. So you get back the guarantees of what you would hope for with the batch gradient descent. Okay, that's the takeaway. Was there a question? Yeah.
What were the actual conditions on the measure T that included finite sums construction?
Oh, I don't know that there were conditions. So the way that these constructions work is that you construct a worst case instance for a given algorithm. So it just so happened that worst case instance required maybe, let's say, a continuous distribution, probably. Other questions? Okay, so here's the outline for today. I'm going to spend the most time on variance reduction because, like I said, that's the most settled currently in optimization. It's kind of like from 2014 to today, it's over. We understand everything. Acceleration and momentum are less understood. Certainly momentum is much less understood. Adaptive step sizes, I wanted to just mention. It's kind of unrelated, but it's also an interesting topic. And I think it's kind of settled for convex problems, but it's pretty unsettled for the cases where most people are interested in them today, which is non-convex problems. So I'll just kind of briefly go through this stuff and spend more time on variance reduction. So the first method I became aware of, I don't think it's the first method that proposed this, but it's the first method I became aware of, and it's one of the most well-known. I'll give you a more complete list of references in a little bit, is the SAG method, Stochastic Average Gradient, by Mark Schmidt, LaRue, and Francis Bach in 2013. So this, as far as I understand it, was a breakthrough in stochastic optimization. I think I was actually at NIPS the year that this was published, if I'm remembering properly. And what's interesting, if you want to follow the trends in optimization in the machine learning community, you should look at what the optimization workshop at NIPS is covering, because that is kind of like what the people are most excited about. And this year was all about variance reduction. So it was kind of like you could see everybody really cared about that. And I believe that this was published in NIPS. So here's the method. It's actually fairly simple. We're going to maintain a table containing something like the most recent gradient, gi, of our function fi. So we're going to have gone through it and drawn functions from our collection, f1 through fn. We're going to have computed gradients, and we're going to store gi, which is a representation for the most recent gradient that we've seen of fi. And we're going to initialize our method by just taking some point x0 and passing through all of our functions and just initializing the GIs with the gradient of our functions at our initial point. So this isn't actually required. They have other initializations that they suggest. Like, for example, you can initialize them at 0. And that leads to some theory that's still fairly strong. But this is maybe the most intuitive initialization. And then here's the method. Just like we would do in SGD, we pick a random function, a random data instance, like in logistic regression. And we set GIK to be the gradient. This should say grad of FIK at xk. We pick some. We just evaluate the gradient of FIK at the point xk minus 1, as we usually would do, and we store that as GIK. And we don't touch the other ones. Okay, so all the other ones remain the same. All the other gradients in our table remain the same. And we make this update. Okay, instead of moving us in, let's say, if we just had GIK at iteration k here, that would be SGD. Okay, if these were actually gradients, this would be full gradient descent. It would be batch gradient descent if these were actual gradients. So instead, I'm going to do something in between, which is that I'm going to actually be using the freshest gradient that I got for GIK and all the old ones for the others. And I'll take the average of all of them in place of the average of the true gradients. Right? Because each of these we're estimating grad fi at some point. And if that point is somehow not, if it wasn't visited super long ago, then it should be pretty close to the gradient of fi at xk minus 1, which would be full gradient descent. So that's the update I make. Okay, let me pause just for a second. Okay, so the basic idea behind SAG can be traced back to actually a method called incremental aggregated gradient from Al Hero and some other people in last decade, 2006. One thing that you'll notice is that the estimates of the gradient, so these guys here, they are no longer unbiased. So SAG is actually a biased method for stochastic optimization. It's not giving you an unbiased estimate of the variance, but has greatly reduced variance, right? You can take a look at this and think this is an average of n things. It's going to be very low in variance. So the other thing you might think is it might be expensive to average all these gradients because we're back to full gradient descent in the sense that the update involves an average of n things. But it's actually the exact same cost as SGD. It's more memory. It requires more memory, but it's the same computational cost modulo the memory as SGD, provided that you just write the update in a clever way. And that's as follows. So take the old table average. So this is what the average would have been at iteration k minus 1. Okay, subtract out the old GIK over n and add in the new GIK over n. That's all that's changed going from iteration k minus 1 to k. This is all we need to do to modify the old average to the new average. Okay, so this let's say we have in hand. So we have available, and this is order 1. So it's the same cost as SGD. It's just an order 1 update. Let me tell you about the theory for SAG first, and then I'll show you an experiment that I did. Okay, so we're in a setting that's, let's say a standard setting for analysis. We have this finite sum, or this average, which is a criterion. Each of these functions is Lipschitz with the gradient is Lipschitz with constant L. And we're going to be denoting the average iterate after k minus 1 iterations as x bar, or actually k iterations once we count the initial iteration as x bar k. Okay, so this is also a very common thing people do with SGD, is because it's not a descent method, we actually average the iterates from over a bunch of iterations and evaluate the criterion on that. An alternative is to look at the best one so far. Okay, it's just because the method is not a descent method, we have to do something else than just track xk itself. So here's a theorem from the SAG paper. If we take a fixed step size, so this is where you should be seeing the difference to SGD is enormous. We're allowed to all of a sudden take fixed step sizes again. We're not diminishing them at all. And now it has to be 1 over 16 times the Lipschitz constant, whereas with full gradient it's just 1 over L. If we initialize SAG in a particular way, which is actually to take centered gradients, so we take the gradients of our initial point and we subtract off the full gradient. So this just makes it so that the average of all of these guys is 0. We've centered them. Then we get the following convergence bound. The expected criterion gap after k iterations is something like n over k times the gap where we started plus L over k times the squared distance between our initial point and x star. Okay, and this expectation is taken over the randomness in the choice of indices. We're drawing indices at random at every step. So let me give you some notes on this. I've stated it for the average iterate, but in the same paper, they prove essentially the same result for the best iterate seen so far. So you don't really need to do averaging. You can also just record the iterate that had the smallest criterion value. There are also bounds for different initializations. If you initialize at 0, there's another bound which is slightly worse. So you don't have to initialize the gradient table according to the theory at these centered initial gradients. In terms of convergence rates, just note that this is 1 over k, which is the same as gradient descent in the same setting under the same assumptions. Whereas SGD would have gotten 1 over the square root of k. Okay, so we've moved from kind of the slow diminishing step sizes rate to the faster but still sublinear rate of gradient descent in this setting. The constants are different. That's somewhat important to note. So after k steps, if you remember the gradient descent bound we derived, it was just this simple L over 2k times this is the squared distance of where we started to a solution. And SAG has two terms. The second term kind of looks like this. Okay, the constant is a half gets replaced by 128. This is somewhat more maybe worrisome, and that this depends on n. Okay, so now we're paying a price of n over k times the criterion difference. So the authors have a bit of follow-up to show that this can be decreased under better initializations. But maybe it's still worth pointing out that we have the same rate, but we now have a term that depends on n. Okay, here's what happened. Oh, before I show you that, I'm going to show you the strong convexity analysis. Sorry, one more theorem before I show you the experiment. Under strong convexity, of course, this is another very important case, perhaps the most important one that people worry about for SGD. If you additionally assume that Fi is strongly convex with parameter m, then SAG gets, with the same step sizes, gets a linear convergence rate. Okay, so it's something to the power of k, or that's something less than 1 times something. And in fact, the scaling with the dependence of this contraction factor on the strong convexity and Lipschitz constants, m and L, is the same as it is for gradient descent. I mean, constants are different, but the scaling is going to be the same. So it shouldn't have, let's say, it shouldn't be affected by conditioning according to the theory much worse than gradient descent. They're both linear. They both have similar contraction factors. Okay, and just to repeat one more time, in this setting, we only get a 1 over k rate for SGD. So this is a huge difference with SAG. So we say, like with gradient descent, we say SAG is adaptive to strong convexity, which means under the same algorithm, in fact, the same step sizes here, goes from a sublinear to a linear rate once we add strong convexity. The proofs of these two results, I guess I just noted here, of this one and this one, they are nothing like the gradient descent proofs or the SGD proofs, and they're very difficult. There's a longer version of the SAG paper that was published after the NIPS conference that provides more of the theory and more comprehensive theory. And if I remember properly, they actually have to use a computer-aided strategy to verify that certain polynomials in this Lyapunov function that they create are non-negative. So they have this strategy for somehow tracking the descent with Lyapunov functions, and some of them they require to be non-negative, so they actually have to use some kind of computer-aided proof for it. So it's very complicated, and it's also not short. My takeaway is that SAG being biased, it actually substantially complicates the proof. So the fact that these gradient updates that we make here are biased, they're not unbiased estimates of the gradient, makes the proof much more complicated. But the results are certainly impressive. So here's what happened. Okay, when I ran SAG versus stochastic gradient descent. I used the same logistic regression example. So I had a n equals 10,000, p equals 20. And I generated 30 random problem instances, so 30 data instances from the same model. And I ran SGD and I ran SAG. And this is what I got. So here's each of these curves. Okay, each of these light red curves is a convergence curve for SGD, and the dark red is the average convergence curve. This is what SAG looks like. So it's kind of strikingly lower variance. Right? It doesn't look anything like SGD at all. It looks pretty much deterministic. Some notes that kind of important. It did not work well for me out of the box. So I went through a lot of various initializations before I got something to work this well. What ended up working for me was to take one full cycle of SGD. So I actually did a vanilla SGD pass over the data, which just costs order n right here, or I guess order n p flops, because we visit one data point at a time, and each one is an order p computation to compute the gradient. And then, to be fair, after that one cycle through the data set, I initialized both SGD and SAG from the same point. So they're both starting from the same initialization. And I initialized the gradient table at the gradients I saw after that one full pass. Okay, that ended up working this well. If I initialized them at 0, or if I initialized them at the gradients, the initial points, or the centered gradients, initial points, I got worse results. It didn't look like it was doing much different than SGD. Tuning the step sizes was also tricky. It was tricky for me to get the step sizes right. This was about as large as possible as I could take it in this experiment before it diverged. And so I actually talked with Mark Schmidt about this. He's the lead author on the SAG paper. And he was the one who I believe gave me the suggestion of taking one full pass over the data set to initialize it better. He conveyed to me that, I don't know that this is necessarily in the papers, but that SAG is going to work particularly well versus SGD for ill-conditioned problems. So you're going to see actually a bigger difference in their performance for ill-conditioned problems, not for nicely conditioned problems like mine. So my X's were IID Gaussian. The entries were IID Gaussian. So this is maybe still not the most favorable case for SAG versus SGD, but you still can see kind of a substantial difference. And remember, these two have the same cost per iteration. They're doing the same complexity. Yeah? That's an interesting point. I don't know. I mean, that may be me taking the step sizes to be a little too large here. I'm not actually sure.
Try to apply this to a problem in practice, like let's say 10 million data points, we have to run it a few times with these step sizes.
Yeah. Well, I guess what I would say is you should use SAGA, which is the next method I'm going to talk about, which is much easier to use. I wouldn't use SAG. Yeah. Is SAG under strong convexity? It is. So under strong convexity, I actually kind of slipped this by you. We don't actually take after some iteration number in strong convexity, it actually is a descent method. We don't actually have to average the iterator or take the best iterator, because the best one is the last. So this is an xk rather than an x bar k. And that kind of slipped by you. I never said anything. So it's a descent method under enough conditions after some iteration. So to go back to Will's point, I think I was probably taking the step size here larger than this. I wasn't computing this. I just was taking them to be as large as I could to get something that looked right. Okay. Follow-up paper on SAG is called SAGA. I'm just going to tell you what it is, then I think it's time for us to take a break. SAGA was the next year. So SAG was 2013, SAGA was 2014. It's a follow-up on the SAG work. I don't actually know what the A stands for. I'm not sure this stands for anything. Yeah, I don't know. It's a follow-up on the stochastic average gradient paper. They actually should have reversed the names because this paper is short and sweet and has simple proofs, and the SAG paper was kind of monstrous proofs. So it would have been better if that was called SAGA. But the method's very similar. It actually differs by such a small amount that you almost feel bad for the authors of SAG who weren't on the SAGA paper. The method is the same. Gradient table, initialize it the same way, etc. And remember where we had we wrote the SAG update like this. Okay, where this is the old average. This was adding and subtracting the new gradient over n. SAGA just doesn't divide by n. It adds and subtracts the gradient itself, not divided by n. Okay, so that's the only difference in the two methods. And it actually makes a huge difference for many reasons. One is that it's actually much higher variance. Now imagine that like these terms that were divided by n, so we're really having an average of things, we're adding and subtracting terms that aren't scaled. These are randomly drawn, so it's much higher variance. The other thing it does for us is it actually makes this update unbiased. It's very surprising, I think, when you look at the first time. It's not a biased update anymore. It's actually a bona fide, unbiased estimate of the gradient. And that makes the analysis much simpler, and I think it tends to make the method work better in practice. So let's take a quick break, and I'll explain to you a bit more about SAGA when we come back. Okay. So let's jump back into SAGA. Once again, it's very similar to the idea of keeping a gradient table and averaging past gradients along with the most current gradient, or these are all estimates of the gradients rather. like we do in SAG, but we add and subtract the most recent gradient itself. We subtract the old gradient and we add the most recent gradient, for example, ik. Whereas SAG would divide these by n, so it would be maintaining truly an average in the end, whereas this is not. So that's the only difference, is whether or not we scale these first two terms by 1 over n or not. Somewhat remarkably, at least I was surprised when I saw this for the first time, this estimate is actually unbiased. It's an unbiased estimate of the gradient. And there's a very simple explanation for that. So we're going to depart a little bit from this specific setting and just consider a kind of generic family of estimators of this form. Okay, where let's suppose that our problem is to estimate the expected value of x, okay, for some random variable x, and I have some other random variable y, which I'm assuming is correlated with x, so it's a good idea to include its information. And I'm going to take the following family of estimators indexed by alpha, a parameter alpha between 0 and 1. It's going to be alpha times x minus y plus the expected value of y. Let's consider those as estimators for the expected value of x. Okay. So let's compute the first two moments of this estimator and see what it looks like in terms of alpha. So the calculation is very easy. If I take the expectation of theta sub alpha, right, then I get simply this. I get it's theta times the expected value of x. Sorry, not theta. Alpha times the expected value of x minus alpha times the expected value of y plus the expected value of y, right, which I had lying around in my expression for theta alpha, which is just alpha expected value of x plus 1 minus alpha expected value of y. Okay, so if y had exactly the same expectation as x, and it was correlated with x, then this would be, I mean, correlated with x, the idea here is that it's a good idea to use it. This would be exactly unbiased for any alpha, but if not, then it's not generally going to be unbiased. Right? We're going to be paying some bias if y didn't have the same expectation as x. Let's look at the second moment now, or the variance. Okay, the variance of this estimator. So the expected value of y, right? It gets dropped here because the constant with respect to this variance operator. The alpha squared comes out, and we get alpha squared times the variance of x minus y. Hopefully people haven't forgotten. Those of you who are statisticians surely have not forgotten this, hopefully. This is just the sum of the variances of x and y minus twice the covariance of x and y. Okay, so we can see that if these are very correlated, and this is very large, this whole thing could have lower variance than x itself, and the expectation could be close to the expectation of x if we chose alpha properly, or if the expectation of y was close to the expectation of x. So this family of estimators, in fact, describes what's happening now. If we look at the saga and the SAG gradient estimates, so let's map x to, let's say, this guy. So remember, the expectation of this guy is truly the full gradient. This is the gradient of a randomly picked instance, and its expectation is truly the full gradient, which is what we're trying to estimate. And we can think about this guy as y, and this guy as the expectation of y. Okay, so Saga uses alpha equals 1. Right? This is x minus y plus expected value of y, but it's multiplying this as 1. SAG uses alpha equals 1 over n. So they're on actually really far ends of the spectrum as to what we could be choosing for alpha. Really, really small for SAG and really, really big for Saga. And they're giving us two different things. When we take alpha equals 1, you can see in our computation for the first moment that this estimator theta alpha is unbiased. Okay, there's no bias whatsoever. Its expectation is just the expectation of x. That's why SAGA is unbiased. SAG uses 1 over n, okay, which actually gives us quite a bit of bias if this is, let's say, very far from the expectation of x. But it has a much smaller variance. The difference in variance is drastic. The variance that we see in SAGA is essentially this term. And in SAG, it's this term multiplied by 1 over n. Okay, so SAGA chooses a large alpha, give us unbiasedness at the cost of higher variance. SAG chooses 1 over n, which is quite biased, but it's much lower variance. The upshot of SAGA, which I'm not showing you because the statements are almost identical to these. The statements are really close to these, is that you get all the same convergence results. So it's really all the same properties theoretically as what you get with SAG. The proofs are much simpler. They're back to being elementary in the sense that, they could be exercises on a homework kind of thing. They're probably a little more complicated than they are for SGD, but they're not much. Versus these proofs, which are, very nasty. Okay. One other thing I'll say about SAGA is that a very nice feature of SAGA is that you can extend it to proximal operations as well. So if I had a case in which the loss was something like the average of Fi plus something non-smooth, then there's a proximal version of SGD we learned, right, where I just replace the gradient by an estimate of the gradient, and I still apply the prox operator. The same can be said of SAGA. We can proximalize it. We get all the same results. So if we have a problem like, likelihood, which is an average of functions, plus some regularizer, and we know the prox that regularizer, we can go back to applying SAGA in place of SGD, get much better conversions. So here's the example for logistic regression. I think it's again fairly striking how differently SAGA and SAG behave. But hopefully my explanation made sense to you, and you can kind of see now why they have such different variances. The same 30 problem instances, the same setup. I'm running SAGA, and now we see it truly has a lot of stochasticity, and it's converging just about as quickly as SAG is. Both are much better than SGD. So I used the same setup to initialize SAGA as I did for SAG, and I took a full pass over the data, and then I initialized all methods from there. But the step sizes were very easy to tune. Like pretty much any step size in the vicinity of 1 over the Lipschitz constant worked fine. And I'll just emphasize once again, like these are like very different methods. Right? This looks almost deterministic. SAGA is truly a stochastic method in some sense. Okay. Any questions about that? Yeah.
Was it SAGA just as sensitive to the initial conditions?
It was still fairly sensitive to initial conditions. Yeah. Yeah. So I'm not exactly sure what the right resolution here is. I think it is fairly reasonable to take one pass of the data set. That's like, I think, something you'd expect to do anyways. So I think that's not a bad initialization in practice. But yeah, I found that worked the best here. So
I have to spell alpha is bigger than 1. Seems like increasing alpha is a good thing.
Well, I guess I've not thought about it. So just off the top of my head, I feel like you would break unbiasedness for sure, and you would also ruin. You're going to see you're inflating the variance here, potentially. Which means that if we took alpha large enough, we could have a method that had higher variance than SGD itself. A little larger than 1, I don't know. SAG is the only method I know of out of many others. So I'll list in a few slides many others that is biased. So there's several others that are variance reducers that are unbiased. SAG is the only one I know of that's biased, and it has the weirdest theory. So I would just venture a guess that alpha a little larger than 1 probably make things complicated, but I don't know. Okay, so here's my slide. There's many others. They have names you're not going to remember, like SDC. Well, maybe you'll remember them. I don't know, but they're hard to remember for me. SDCA, SVRG, S2GD, Meso, Finito. They all came out around the same time, so around 2013, 2014. And as far as I understand, hopefully I'm not offending any author who's contributed to this body of work, Saga pretty much wraps it up. Like once you read the Saga paper, it extends to proximal functions. It's simple, has all the same guarantees. I think it's kind of like the method that I would remember, unbiased. Another property that's nice about it. I'm sure that there still could be gems in these papers that's like nice insights. I just think that from a kind of practical standpoint moving forward, I think Saga is a pretty good method to remember. And both of these papers do a really good job of reviewing the literature, so they talk about all these methods in case you're curious. And some of these come from very different directions. They don't come from the same direction as Saga or Saga at all. They'll look like very different methods. So for that reason, it might be interested to look at if you're curious about variance reduction. So let's talk about optimality. And this is something that actually has changed since the last time I taught this. So I taught this in 2014, which is right when all these methods came out. I gave a lecture that was kind of like this. And at that time, there was more excitement about these methods. I think now there's a bit less because the story has pretty much been settled. But this is new since then, is optimality. So at the time, it was believed that still these methods were not optimal. So it was believed that there were lower bounds that were strictly smaller than the upper bounds you saw in SAG and Saga, and it did not have to do with matching condition numbers. There was something else that was missing. Since then, that paper, which I won't name, was actually found to contain bugs. So the story has changed quite a bit, and these methods, with kind of a somewhat smallish tweak in terms of acceleration, these methods are actually now known to be optimal. So we have a nice optimality theory for stochastic optimization, finite sums, just like we do for deterministic first-order methods. Remember, so for deterministic first-order methods, we saw with the upper bounds from gradient descent, and with acceleration, we can achieve the lower bounds that are known for first-order methods. We have complementary theory for convex finite sums, okay, for stochastic optimization. And if you were to dig a bit into the bounds that I showed you, let's say for the strongly convex case as an example, if you write in terms of the epsilon notation, this is what we see in terms of convergence. The upper bound is n plus L over m times log 1 over epsilon. That's how many iterations you need to get an epsilon suboptimal solution. And the lower bound that's come out in 2015 and 2016 looks similar, except essentially we replace L over m by the square root of L over m. So it's a better dependence on the conditioning. And it's now known that we can accelerate these methods, just like we can use Nesterov acceleration in the full batch setting to achieve this optimal convergence, both in terms of epsilon and the condition numbers. Okay, so there's some nice papers here that show you that, but I'm just skipping the details because I think this is interesting, but it's somehow less of a departure from what you've seen. This is applying acceleration. Okay, so now comes the rest of the stuff I want to talk about. Like I said, I want to spend the most time on variance reduction because that's the most complete story, and hopefully that wraps it up in terms of that stuff. The story beyond variance reduction acceleration for finite sums becomes very complicated. So for convex problems where you have a stochastic problem, your criterion is the average of functions. Everything at this point has been pretty much settled, just like it has been for first-order methods in the batch setting for a while. If we move out to the more general stochastic picture, so we look at our criterion being expectation of functions rather than an average, I'll just remind you that the performance of SGD cannot be improved. So this kind of variance reduction stuff, in principle, does not do anything once we have a more general stochastic setting. because we have lower bounds due to Nemirovsky and others that match the performance of SGD. So in ML, we tend to care less about stochastic optimization potentially. I mean, if we have, in a truly general setting where our criterion is like this, right, it's an expectation over some randomization variable of a function like this. We tend to think more about finite sums, but in optimization, in the operations research community, for example, this problem is studied greatly, and their SGD cannot be improved. Okay, I'll just remind you of that. For non-convex problems is where things become really murky. I mean, things are murky for non-convex problems in general in other ways, but I'll mention this now because it's a very active topic of research. So just as an editorial comment, which I didn't put in the slides because I don't know that this is more of a heuristic opinion, variance reduction for non-convex problems is not studied. And I think heuristically, many people who work on non-convex stochastic optimization think of variance reduction as kind of the wrong idea. So for a convex case, you want to reduce variance in the gradient estimates. That's only hurting you, right? You're not taking the full gradient because of computational reasons. And anything you're doing to approximate it, you encounter variance, you want to reduce it. In the non-convex setting, it's not clear at all that variance reduction is a good idea, because actually variance can help, right? Variance can help you get out of a local minimum, for example. For example, if there's a descent direction, and you're in let's say a point where the gradient is 0, or where you're close to the point where the gradient is 0, you maybe want enough variance to move out of that saddle point. So variance reduction is not necessarily a good idea. Acceleration is an idea that's very popular and has a lot of following for non-convex problems, but it services in a slightly different way. It presents itself in terms of a method called momentum rather than Nesterov acceleration. Although I think even Nesterov's acceleration is being carried over as well in the non-convex setting. Just that momentum tends to be more popular. So momentum, just to give you a bit of history, predates acceleration by nearly 2 decades. So Polyak is he's one of the kind of giant figures in optimization who predated Nesterov by nearly 2 decades in terms of this work. And the idea is quite simple. He invented a method called the heavy ball method that is still used somewhat widely in practice for non-convex stochastic optimization, in which instead of taking, let's say, an SGD update like this, so x minus tk grad fik of x, we add a term that pushes us in the direction that we were going. So for some fixed constant alpha. This is a momentum term. It actually is somewhat similar to Nesterov's acceleration. I showed you Nesterov's acceleration for functions whose gradient is Lipschitz. That's the one that gets the 1 over k squared rate that you saw. For strongly convex functions, Nesterov has a different method for acceleration that looks very much like this, but there's a gradient correction. There's something different that happens here. So they actually look quite similar, but this is much older. This can work really well in practice, and I think a lot of people currently are interested in finding out why and when this works, because it can also be somewhat fragile. So I'm showing you what happens even for a convex problem. So this is just a convex quadratic, the difference between the heavy ball method and Nesterov acceleration. So they start off quite similar, and these are what I told you at one point were called Nesterov ripples, these little bumps here. After about iteration, well, certainly 50, but earlier than that, Nesterov becomes a descent method. And this is very typical in the strongly convex case. Okay, the heavy ball method never does. It bounces around forever, essentially. And now you can imagine applying this to a non-convex problem. If you can't attenuate the variance at all, it can be very fragile, right? So there is currently a lot of work trying to figure out kind of when and why this works for non-convex problems. I hope that a couple of years this will be settled enough that we can do a full lecture on it, but at this point it's not really. So the last thing I want to talk about in the 10 minutes I have, unless there were questions about that at all, was adaptive step sizes. So this is also a very big topic actually it's big both in convex and non-convex stochastic optimization. And it does something different than either of the things you've seen so far, which is variance reduction and momentum. So I wanted to at least mention it. And to motivate it, we're going to look at a very concrete problem instance for logistic regression. So let's suppose that you had a bunch of data. Every data point was a movie review, and you wanted to classify whether or not the movie review was positive or negative in sentiment. So your YI was this a favorable review? Did the critic say something nice about the movie, or was it a negative one? And the features are, you have one variable per word in some gigantic dictionary, and let's say xij counts the number of times that the jth word appears in the ith review. Okay, so here's an example review. I just actually Stochastic gave me this, so I assume it's a real movie review. Piece of subtle art, maybe a masterpiece, doubtlessly a special story about the ambiguity of existence. So I think it sounds positive to us, but you can imagine that somehow it's to build a classifier from logistic regression. It's certainly non-trivial. So there's an important feature of this problem that I highlighted, which is that there are some words that are, let's say, common and uninformative. So that's what I highlighted in blue, like maybe, about, the, of, a. And those don't, the number of times they appear in a review or whether they appear at all is not really that informative. There are some words that are rare and uninformative. Okay, like maybe ambiguity and existence are somewhat rare, but they're not alone that informative, right? And there's some words that are rare and informative, like masterpiece and special and subtle and art. Okay, so it's these words we want to be picking up somehow in our classifier. If these words have some, if I have an instance which has xij equal to 1 for some of these rare informative words, I want those to be dictating my decision for the classification boundary. Okay, so let's take a look at the gradient of a particular example in the logistic loss. Right, I look at the ith training example, I take the gradient, it's exactly this. It's minus yi plus 1 over the probability I would assign somehow to that point xi having a positive review under the logistic model. That's this. Or not 1 over the probability, this is the probability. So it's 1 over 1 plus e to the minus xi transpose beta times xi. That's the gradient of the ith training example. And there's an observation here, which is that if xij is 0, okay, so if I didn't see the jth word in this ith training example, then the jth component of this gradient would be 0. Which means that if I was looking at a rare word that was informative, okay, which had xij equals 0 for many instances, right, for many instances I, then for most of the SGD updates, I would not be moving beta j at all, right, because the gradient in the jth component is going to be 0, because I'm looking at all these instances where that word didn't appear, and I learn these rare features very, very slowly. Right, SGD just essentially can't budge beta j because the gradient is 0 in the jth component. So SGD does two things that hurt us here. The first is that it gives kind of equal weight to common and rare informative features in terms of how it just multiplies this gradient by a step size. So it multiplies every component by the same step size. So we have no difference between the weight we're applying to common and rare words that are informative. And because we're diminishing the step sizes, if it takes us a while to find a rare word, so suppose we had to go through many instances to find a rare word, then at that point the step size is going to be so small that we're going to move beta j very little. So if it actually was a very informative word and it needed to have a large coefficient, we take a very long time to learn that. So to escape this long wait, we're going to have to do something more adaptive. We're going to have SGD adapt to the geometry of our problem, in which we learn that somehow there are some aspects of the gradient that are large and helpful. And the way to do that, I guess the first method to do that successfully was Adagrad by John Ducci and Elad Hazan and Yoram Singer in 2010. And it's a very popular method nowadays, although I think for deep nets people use some variants that are a little different. But Adagrad was somehow, let's say, the first adaptive method to have really solid theory. And here's the method. It's actually quite simple. We take a typical stochastic gradient descent update, okay, in which we pull a random instance. We look at the gradient for that instance, And instead of just doing x equals the previous x minus something times g, we actually have a different step size for every component. So if we have if our optimization variable is p-dimensional, we have a different step size for essentially for every dimension. And it has to do with the norm of past gradients in that dimension. Okay, so we basically scale how much we take, how big a step we take in the jth component by the norm of the past gradients in that component that we've seen so far. And this alpha is a prefixed constant. It's not sent to 0 like you would be doing in SGD. So it's quite different in that regard, alpha being fixed. The learning rate of informative features diminishes slowly. That's the point of autograd, is that for sparse problems, we've somehow positioned ourselves so that we're diminishing the learning rate of the informative features slowly, and we're diminishing the learning rate of the other features less slowly. You can see really huge improvements over SGD in sparse problems, so this can be a really big difference. And for a lot of problems, particularly in NLP, my impression is that autograd, but when it came out, was a huge boost in terms over SGD in terms of the types of problems people were looking at. And I guess it's worth saying that in some instances you can actually do worse than SGD. So it's not a win overall. It's more designed for sparse problems. And there are more recent variations like ATOM and RMS prop and NATOM and other ones, etc., that are very popular now for training deep nets that use a similar idea of adaptive step sizes. Was there a question somewhere? Yeah.
Yeah, I think this is what happens the first time around. Like you just ignore the denominator just because the sum would be 0, right? Or would be 1 basically. You just go up without way out.
That's a good question. I guess we could do something similar. We could initialize these. We could initialize somehow to be the gradient at the initial point. Then it would all be non-zero. It helps to, it kind of helps to look at autograd in this regard. So let's just compare, let's forget about stochasticity for now. This hopefully will motivate a bit where it comes from. Let's compare gradient descent to something like quasi-Newton. What do we call this? We call this maybe H inverse. Right. So if I had a working Hessian H, this would be like a quasi-Newton method, like we had a lecture on. This is the actual Hessian. This would be Newton's method. Autograd does two things. First is that it says, let me approximate the Hessian by the outer products, of gradients. This should say that I've seen so far. Okay, so there are reasons you might think this is a good approximation to the Hessian. Some of the motivation for autograd comes from mirror descent, which you'll learn next time, and the fact that it adapts to the geometry of the problem, that this actually approximates the Hessian in some decent way. There also is a kind of a statistical reason why you might think this is the case based on likelihood theory, but I won't go into that. What autograd does is actually, instead of just taking this approximation to the Hessian itself, it takes the diagonal of this. Or maybe it actually takes the square root of the diagonal. Okay, which you can see that the diagonal is just the sum of the squares of the gradients that I've seen across the dimensions. This being much more computationally convenient. The autograd paper also analyzes the kind of the full version and gives theory for this, but that just costs more. So it's just using a diagonal adaptation. And where autograd can really improve, this may be my last little bit I say about it, is if you look at a convex problem, if you look at our let's say our SGD, or our gradient descent bound, it looked something like r over the square root of k times the Lipschitz constant. This was our upper bound that we got from analyzing, in fact, the subgradient method, which is the same analysis for SGD and for gradient descent in this case, where r was the distance between the point we started and a solution. And so you might think about r as scaling like, let's say in p dimensions, square root of p. Right? Because let's say I have some bounded, if I'm working on a bounded domain, then the distance I can think about between any initial point and my solution is going to be like square root of p. So I should think about gradient descent as converging like square root of p over k. So that's the dimension of my optimization variable. What Adagrad does, okay, in the sparse case, is that it brings this down to log p, or I think actually even root log p over k in the sparse case. Okay, by adapting better to the geometry of the problem. In the worst case, okay, if the problem isn't sparse and you want Adagrad, I believe the bounds are actually worse than square root of p. So you get something worse than SGD. I don't think it's always a win. All right, so that's just a flavor of what people care about now, and hope some of that was interesting. On Wednesday, you'll learn mirror descent, and then next Monday will be like our Ask Me Anything recap kind of lecture. So, all right, I'll see you guys on Wednesday.